Okay, good morning, everyone. So last time we started talking about identical particles, and let's say we have n of them. So for n identical particles, and we can assume that we can label these particles by their complete set of commuting observable labels, which we are generically calling alpha. So if I have alpha sub I, that's supposed to represent a complete set of commuting observable labels for the individual particles. And so the idea is we can choose such a labeling, but then the answers can't depend on our choice. So for individual particles I, and I therefore runs from 1 up to n. And then there's some basis of kets for the system that you get by taking the tensor product of all the alphas. Okay, so now let me introduce the concept of a pair exchange operator. So the pair exchange operator is just defined in such a way that whatever it acts on, it interchanges the labels. So I'll call it P sub ij. P sub ij acting on a state where the ith label was alpha I and the jth label was alpha j, just gives back a state where the ith label is now alpha j, and the jth label is alpha I from the original state. Okay, so for example, if there are only two particles, then it just interchanges the two labels. But if there are more than two, it leaves the other ones alone. So acting on a state alpha 1, alpha 2, we get back alpha 2, alpha 1. Okay, now last time what we said is that observables have to be symmetric under the interchange of labels. And since that's true, since observables, and I'm going to be generically calling our observable A, are symmetric under interchange of labels, meaning we can't tell the particles apart, then Pij acting on A has to equal A times Pij. In other words, they commute, and that's true for any I and j. So this is for any pair exchange operator Pij and observable A. So let's prove this. As with most proofs in quantum mechanics, it only takes a few lines. So proof. Let's write our operator in the following form. This is an operator that's acting on a ket space that has n individual particles. So we can write it as something that acts on the first particle, something that acts on the second particle, up to something acting on the nth particle. Okay, so where the little a's, I'm violating the usual rule in this class that capital letters are for operators. The little ai's are operators acting on the individual kets. So the kets for the individual particles. Okay, so now let's just compute Pij acting on this A. And I'm just going to distinguish here the labels for the ith and the jth particle that we've chosen. And the same thing for a state that it's acting on. Okay, and now according to the definition of a permutation or a pair exchange operator, Pij is just supposed to interchange the labels of everything that it's acting on. So everything to the right of that. So this becomes A, Aj, Ai, and also alpha J, alpha I. And all the labels indicated by the dots are unaffected. Okay, and now this state I can rewrite in terms of the pair exchange operator. This is Pij acting on alpha I, alpha J, back again. Okay, and so now if I compare what I've got here, I've got in both cases, the first line and the last line, I'm acting on the same state. And that's supposed to be a set of basis states. So if it's true for a set of basis states, it has to be true for the operators. And so this right here has to equal this right here. Okay, and so we can conclude, well, I guess there's one more ingredient here. So we notice that this has to be AI, Aj, because it's symmetric. That's the assumption we're making. And so from the assumption that the observable has to be symmetric, we can conclude that Pij, A has to equal APij, acting on every basis element. And if it's true acting on every basis element, then it has to be true on the whole state space, on the whole ket space. Okay, so in particular, we're often particularly interested in the Hamiltonian. So the Hamiltonian, we have learned, must commute with every pair exchange operator.
Professor?
Yes.
I'm sorry I fell behind again. What was that symmetric in that arrow for?
So that's saying that this and this are the same thing.
Okay, thank you.
So the Hamiltonian must commute with every pair exchange operator, because we just chose one at random. We could have chosen any one of them. And so you can write Hamiltonian commutator pair exchange operator is 0. Okay, so that allows us to prove something interesting. So now suppose that you've got a set of states, you've chosen your set of states so that this one, for example, is an energy eigenstate of the whole Hamiltonian. And let's call its energy E. And so what we're about to show is that there's some degeneracy. And again, this is going to be a one-line proof. So Hamiltonian acting on pair exchange operator acting on our energy eigenstate. Because the Hamiltonian and the pair exchange operator commute, I can just rewrite this like this. And then the Hamiltonian acting on that state is E. So I can write this as E. Okay, and let me draw parentheses around that, because that means what we've learned is we started with this state indicated by the dot, dot, dots that was an energy eigenstate with energy E. And now we found another state that also has energy E, energy eigenvalue E. And so what that's telling us is that all kets related by pair exchange, and by doing multiple pair exchange, you can do permutations of more than one particle. So all kets related by pair exchange of identical particles. Of course, nothing we're writing here is true if the particles aren't truly identical, because then we can't assume that the observables have to be invariant under interchange. So these are degenerate, and this is called degenerate in energy, and this is called exchange degeneracy. Okay, so the most important thing you have to realize about exchange degeneracy is that it's mathematically true and it's physically a complete fake. So this is fake physically. Okay, and so just for example, let's say we only have two particles. To understand why this is a fake, if I have two identical particles, then the two states that are supposedly degenerate in energy are alpha 1, alpha 2, and alpha 2, alpha 1. Okay, or any linear combination. Have the same energy. That's true. But this applies only to the mathematical kets, not the physical states. So degeneracy only applies to mathematical kets. Not to physical states. And that's one reason why it's useful to distinguish between kets and states, which we've been a little bit sloppy about up till now. So here's the claim that supposedly makes this true, is that physical states are eigenstates of pair exchange operators. As opposed to the kets, which don't necessarily have to be. And they have to be eigenstates of all pair exchange operators at the same time. So at this point, right at the moment, I'm not giving you any epistemological reason why this has to be true. But before we get to that, we can ask the question, if they're eigenstates of all pair exchange operators, what are the possible eigenvalues that they can have? Okay, so what are possible eigenvalues if I'm claiming they're eigenstates? And to find out, we just note that if we do a pair exchange on I and j, and then I do it again, I've just gotten back to the same state for sure. So the pair exchange operator squared, this is true for any I and j, has to be the identity operator. And so if I claim I've got an eigenstate psi of a pair exchange operator with eigenvalue lambda, if I just take that equation and act with Pij on it again, I get lambda squared, which has to be the same state. So I must have lambda squared equals 1. Okay, notice it's not lambda times lambda star. This is really lambda squared. And the only algebraic solution to that is lambda squared is plus or minus 1. So it can't be a phase like for a unitary operator. It's really plus or minus 1. Okay, so now I said as a claim that the physical states are eigenstates of all pair exchange operators at the same time. And we can make that more formal now by calling it a postulate. So the postulate is physical states as opposed to just mathematical kets that I could write down. Physical states have eigenvalue plus 1 for all pair exchange operators. For identical bosons. Okay, and bosons are defined to be ones with integer spin. And they have eigenvalue minus 1 for all identical fermions. So that's spin 1/2, 3/2, 5/2, etc.
Professor, wasn't that supposed to be lambda equals to positive negative 1?
Oh, yeah, very good. Oops. Thank you. So you might say now, wait a minute, back in chapter 3 of the notes, we supposedly wrote down the postulates of quantum mechanics, and we didn't write this one down. Why did you lie to us then? Why didn't you tell us about this postulate? And one answer to that is that at a deep level, this is actually not a postulate. So it turns out, I'm going to put this in parentheses, that you can prove this rather than taking it as a postulate if you do relativistic quantum mechanics. So this can be proved in relativistic quantum theory. And so you don't need to take it as a postulate in that case. But in this course, we are not basing anything on assuming relativity. And more generally, you could assume that, for example, relativity was wrong or something. You wouldn't want to do that because the evidence for relativity is, of course, very strong. But in general, suppose I just want to imagine a universe that doesn't have relativity built into it. And then you would either have to take this as a postulate, or you could just take it as something that there is overwhelming experimental evidence for. Okay, so for us, we'll treat it as a postulate for now on. We won't question where it comes from. So for us, this is a postulate. But that's why I didn't, and most people do not include it among, when you're writing down what are the fundamental postulates of quantum mechanics, you don't include this one. Okay, in any case, we're just now, from now on, just going to assume it's true. And so what we're saying here is that Pij acting on any state with n identical bosons has to give you back exactly the same thing. And Pij acting on n identical fermions has to do the same thing with a minus sign. Okay, and then this is a constraint that you have to impose on would-be states. So if I give you a ket and ask, is it a physical state, and it doesn't obey this, then you throw it away. It's mathematically an okay ket, but physically it's not acceptable. So this completely eliminates the would-be exchange degeneracy, which is a mathematical degeneracy, but not a physical one. So this completely eliminates the would-be exchange degeneracy. That doesn't mean the exchange degeneracy, I'll put it in quotes because it's not really a physical degeneracy. That doesn't mean it's useless. It's useful because when you're just doing mathematical operations on kets, you want to see this degeneracy to make sure you're doing everything okay. So in particular, for two identical particles, we're going to be treating the helium atom, for which this is an example, where they're fermions, but P12 in that case is the only pair exchange operator there is, and acting on alpha 1, alpha 2, that gives alpha 2, alpha 1. Okay, and this is not an eigenstate of the pair exchange operator, and so it's not allowed as a physical state unless the labels alpha 1 and alpha 2 happen to be the same. So unless alpha 2 and alpha 1 happen to be the same, then it is a physical state. And the same thing with alpha 2, alpha 1. Okay, that just writing down what it is shows that it's not an eigenstate. Okay, but one linear combination of them is an eigenstate of the permutation of the pair exchange operator. But which one it is depends on whether the particles that are identical are bosons or fermions. So you can take the symmetric combination. And if I normalize it, I need a 1 over square root of 2, assuming my original kets were normalized. Okay, so this ket has lambda equals 1. And this is physical if and only the states were bosons. And the antisymmetric combination, just the same thing, but with a minus sign. That has eigenvalue -1, and that's physical if they're fermions. So you get one or the other, and you only get that one linear combination as a physical state. All the other linear combinations are disallowed. Okay, so note that in particular, if alpha 1 does happen to equal alpha 2, then the symmetric combination means that I shouldn't have written the 1 over square root of 2. I should have just written alpha 1, alpha 1. Okay, and that has definitely lambda equals +1. So that's definitely can only be a boson state because the antisymmetric linear combination is just the null ket, which is definitely not a physical state. That's one of the postulates of quantum mechanics, is that physical states are non-null kets. So there's no physical state like that for fermions. So this is the Pauli exclusion principle. It follows from the more general requirement that we've made on these states. So this is Pauli exclusion. Okay, and one colloquially says, two identical fermions are not allowed to be in the same state. But more precisely, what that means is for them to be in the same state means they have the same eigenvalues for a complete set of commuting observables. Okay, so that's for two particles. What about 3 particles? Once again, there will be a single linear combination that satisfies the last postulate. And we can just write down what that linear combination is. If you require that the eigenvalue be +1, then it's the totally symmetric combination, which now requires a 1/√6. And so what I can do is just write down one representative ket that has those complete set of commuting observable
Sorry,
labels.
Professor?
And then I have to take every different combination of them.
Professor?
Yes.
I'm sorry, I'm just a little slow in writing. Could you just scroll up a tad bit? Thank you. Thank you.
Okay, so we take every linear combination of these. I'm attempting to make sure I don't write the same one twice. There should be 6 of them. Let's see, 1, 2, 3, 1, 3, 2, 2, 3, 1, 2, 1, 3, 3, 1, 2, 3, 2, 1. Good. So that would be for bosons. And so what I've done to arrive at this thing and make sure it's unique is not only is it the same symmetric if I interchange 1 and 2, but it's symmetric if I interchange 1 and 3 or 2 and 3. And so that completely fixes everything to have the same number in front of it. And then the 1/√6 is just normalization. Okay, and then the other thing I can do is I can require that there be a minus sign when I interchange any 2 particles. And so I can write down the same 6 kets, but now I just write a minus sign if I've interchanged an odd number compared to the first ket. So hopefully I'm getting all the minus signs right here.
Professor, I apologize. I don't want to interrupt you again. Where did that parentheses end? Right after the Pauli exclusion principle?
Let's say it ends there.
Thank you.
Okay. All right, alpha. Oh, I did this wrong. Let's see. That should be 1, 3. 1, 2, 3, 1, 3, 2, 2, 3, 1, 2, 1, 3. And then there's 3, 1, 2. And 3, 2, 1. Okay, and that's the unique linear combination that works for fermions. So once you choose your labels, your alpha labels, there's always a single linear combination that works, that obeys all the symmetry or antisymmetry properties. And therefore, your exchange degeneracy is always reduced to a single state. Okay, now that was 2 and 3. What if you had n identical particles? We would like a way to be able to write this down systematically. So for n identical particles, okay, for the symmetric case, what we're supposed to do is, first of all, there's going to be a normalization factor that's going to be 1/√n factorial. And the reason for that is if I start off with one particular set of labels, and then ask how many different kets can I write down that have exactly those set of labels, but permuted in every possible way, there will be n factorial of them total. And so I'm going to write here plus every possible permutation. And there are n factorial total of them. just counting what they are. And then if I do the same thing for the antisymmetric version, it's the same thing, but with some minus signs sprinkled in. And if you look at where the minus signs are sprinkled in, it turns out to be, you can write this as a determinant, where the determinant is in terms of individual particle states. The first row of them are all alpha 1s. But then I distinguish them by putting another label saying which slot in the total state that's a tensor product I'm going to put it in. And that's 1 up to n. Then in the second row of the determinant, I put all alpha 2s. Okay, but once again, I put another label to say which slot in the final tensor product I'm going to put it in, and I keep doing that till I get to alpha n. Okay, and then I take the determinant where multiplying in the determinant means in the end, I just put it into a tensor product. So this is called a Slater determinant. It's just a way of constructing our antisymmetric state. Okay, we could just do it like up here and just figure out where all the minus signs go. But if we write it as the determinant, that automatically fixes the minus signs to be in the correct spots. Okay, so when you're done taking the determinant, you are instructed to interpret alpha I1, alpha J2, up to alpha K n as the tensor product ket alpha 1, alpha 2, up to alpha K, like so. Okay, so that works for all identical particles, except that when we've done that, we've assumed all the alphas are different, and the combinatorics is slightly different if the alphas aren't all different, which can indeed happen. So this assumes all the alpha I are different. And so you could ask, what happens if one or more of them are the same? So that just means they're the same labels for some complete set of commuting observables for a single particle. This is very commonly going to happen for particles bound in some potentials. For example, if I put things in a Coulomb potential, right, the lowest energy state, there's only one of them. And so like for the hydrogen atom or for a hydrogen-like atom. And so it might very well be that the particles want to be in that lowest energy state, all other things being equal. Okay, but then if I do that, I find out that the antisymmetric combination as a ket is just 0. And so as a state, it does not exist. If any two of them are the same. Okay, so if two or more alpha I are the same. So that's the Pauli exclusion principle again. We often say in the same state, but what we really mean is with the same set of complete set of commuting observable labels. And then for the symmetric case, it's not, there's nothing wrong with this. It's not the null ket, but the combinatorics just affects the normalization. And so instead of a square root of 1 over n factorial, I have to put in the numerator a bunch of factorials that are just however many times each one of the labels is repeated. Okay, and now I write down my first ket for example. And then I write down all pair exchanges or permutations of that ket, but you remove all the redundancies. So all permutations with redundancies removed. And there will be redundancies if the alphas are the same. Okay, and then to compensate, so you can think of these factorials in the numerator, is that they are there to compensate for the fact that when I wrote down all my permutations, I removed the ones that are the same. Okay, and so that's, let's see, this is for fermions, and the symmetric, of course, from our postulate is for bosons. Okay, and these rules apply even if your particles are themselves made out of smaller particles. So these rules apply even for composite bosons. So examples of composite bosons are pi mesons. They are made out of quark and anti-quark pairs, and helium-4 nuclei, and the hydrogen atom. Taken together, the electron and the proton make a boson. So the hydrogen atom is a boson, even though the electron and the proton within it are both fermions. Okay, so that's true, and it's also true for composite fermions. For which examples would be the proton, the neutron, those are made out of quarks, helium-3 nuclei, and many others. Okay, so for a while, let's go back to the case of a 2-electron system. We're going to be talking about atomic physics shortly in the next few lectures. So this is a special case of that applied to helium. So this would be helium atoms. And so when I say that, I really mean just the electron part of the helium atom. So let's write down basis kets for such a system. Okay, so generically, of course, we're still writing alpha 1 and alpha 2. But more specifically, we can label the first electron to have position vector R1 and z component of its spin M1, and the second one to be R2 and z component of its spin M2. And we know that they're electrons, so M1 and M2 can be either plus or minus 1/2 once we've chosen a z-axis. Or we can write this as up arrow and down arrow. That's synonymous when we quantize the spin. So for quantization of S sub z. And so that means our total wave function we can write like this. And I'm going to be saying wave function, but what I really mean is a hybrid between wave functions and kets. So let me call it capital psi, where I put little bars on the side to make it a capital. I can write this in the following way. There's a wave function that I'm going to call 0, 0. It depends on the position coordinates of both my electrons. But now I'm going to multiply by chi 0, 0, which is going to be a particular spin component ket. And then I'm going to basically do this for every possible spin component kets that I can think of. So it's sum over m sub s is minus 1 to 1, psi 1 m sub s. Okay, and now there's a chi 1 m sub s. So what I'm doing is I'm splitting my state up into spin parts and spatial parts. So the chi's are the spin parts. Actually, they're going to be kets, not wave functions. And let me tell you what they are. So chi 0, 0, I'm defining to be 1 over square root of 2, up arrow, down arrow, minus down arrow, up arrow. Okay, and remember when we added spin angular momentum in the last semester, we found out that this has total spin quantum number. Remember, the total spin is just the individual spins summed together. And the quantum number eigenvalue for s squared is 0 for this state. And so s is equal to 0. And notice this combination is antisymmetric. Okay, and then the chi's are just what you get by adding angular momentum. So the 1, 1 is when they're both pointing up. And the 1 minus 1 is when they're both pointing down. And the 1, 0 is the combination that has total spin projected onto the z-axis 0, but total angular momentum 1. Okay, and so these are the states with total spin quantum number 1. The z component is 1, minus 1, or 0. And this, therefore, is a triplet of states. That just means there's 3 of them. And they are symmetric. All 3 of them are symmetric if I interchange the labels. Okay, which just means if I interchange up arrow and up arrow, of course, that's the same. And if I do up arrow and down arrow, and here, if I interchange up arrow and down arrow, this thing gets exchanged into that, and vice versa with a plus sign. Okay, so what I've done is I've separated out together all of these make a basis for all the possible spins of the system. And so for each one of them, I've multiplied by a corresponding spatial wave function. Okay, and so that will be a basis for the whole state space of the system. But we have to be careful to apply our postulate about symmetrization, or in this case, anti-symmetrization. So since the total state must be antisymmetric, because electrons are fermions and they're the identical particles here. Okay, so antisymmetric. That means if I look at just this one where this is already antisymmetric, then this will have to be symmetric to make it work. And if I look at this term where this is already symmetric, then the thing multiplying it has to be antisymmetric under interchange of the labels. So what we learned from that is for this to be antisymmetric, the wave function 0, 0 has to give back the same thing if I interchange R2 and R1. Okay, so what that's saying is that 2 electrons can live in the same spatial wave function as long as their spins are antisymmetric. And conversely, they can live in the antisymmetric combination of the spatial wave function, but only if the spins are symmetric. Okay, so this is the symmetric spatial wave function. Okay, and there's one of them. And this is the antisymmetric spatial wave function for the triplet. So in this way of thinking about it, there are really, for 2 electrons, there are 4 different spatial wave functions. But for each one of them, you have to pair it with the corresponding spin state in order to not be making a mistake. So another way of saying this is that when you consider your pair exchange operators, you can write for them. In this case, there's only 2 particles. So P12, the total pair exchange operator, is a space part or spatial part multiplied by a spin part. And so when you operate on any state, you have to do both of those at the same time. Okay, not only that, but you can actually, in this case, and this is basically true for lots of other cases too, but we typically won't need to do it. You can write down what these operators are more specifically. So note that if I really want P1 to spin, I can write it as 1/2 1 plus 4 over h bar squared S1 dot S2. So I've now written that operator in terms of the defining operators of the spins. Okay, and why is that true? You can just sort of consider it on a case-by-case basis, because if you have S1 dot S2, that's equal to, for the triplet, it's h bar squared over 4, because S equals 1. And for the singlet, it's minus 3 h bar squared over 4 for S equals 0. And that's for the singlet. So that tells you whether you're going to get, when you plug into the preceding formula, that just tells you whether you're going to get a +1 or a -1 for your P12 spin acting on that spin state. Okay, now one of the reasons we care about this is what happens if the total spin commutes with a Hamiltonian, which is often true, but not always. So if total spin S1 plus S2 commutes with the hydrogen atom, all right, often true, then that means that since we have 2 operators that commute, we can choose our eigenstates to be eigenstates of both at the same time. And then we can label our states, our energy eigenstates, by their total spin. And so they will be either S equals 1 states or S equals 0 states. Now, before we go on, we're going to sort of assume this going forward, but it's important to realize when it's not true. So one case where it's not true is the spin-orbit coupling in the fine structure. So not true for spin-orbit couplings. Because the spin-orbit coupling is S dot L, right? And so the spin-orbit coupling, if I commute that with different components of S with that, I will get the corresponding component of L, and so it won't be true. Okay, now fortunately, spin-orbit couplings you can often treat as a small perturbation. And so if you do that, then your unperturbed states will be common eigenstates of energy and total spin. And then you'll see them get split apart by the spin-orbit couplets, which is basically what we already saw happen in the case of the hydrogen atom. Okay, so that's probably actually a good time to stop. We'll consider more about two electron systems and their properties and how to think about them in terms of splitting between perturbation between a perturbed and an unperturbed part next time. I should mention that next week from today is going to be our first midterm of the semester. Most of you have had me before, so you kind of know what the exams will look like. Basically, you get to bring in, let's say, 2 sheets of paper with anything you want written in your own handwriting. It will be closed notes, though, and closed any other books. There will be no electronic devices. On Wednesday, I'll give a complete listing of the rules, but if you've taken the class before, you know what it's going to be pretty much. I will attempt to make it be an exam that's doable within an hour. And it will be based heavily on the homework set. And really, if you think about what we've covered in this class so far, that's going to be perturbation theory and variational principle. So the stuff that we're doing now on identical particles will not show up on this midterm, but will, of course, show up on the next midterm. Okay, so are there any questions about that? As I said, next time I will send out a much more specific, I'll put out a sheet of the rules that are much more specific than that. Okay, any questions on today's lecture? All right, if not, then we will continue with identical electrons next time.
Professor, I do have a question regarding the midterm. Will we be allowed to bring in the notes from last semester's midterms or no?
You can bring in anything you want as long as it's within the length limit of 2 sheets in your own handwriting.
Front and back 2 sheets?
I think I was going to say, let me think about that some more. I'll be more specific next time, but I think it's going to be 1 side, 2 sheets.
Okay, thank you.
Sure.